Hi, we are discussing time evolution in quantum mechanics. In the previous class, we introduced the time evolution operator. Okay, we introduced it as the operator that connects alpha comma t0 at time t with alpha comma t0. Okay, so this is the initial state, this is the time evolved state, and we said that there has to be an operator, or we assumed that there's an operator that connects these two states, that relates these two states. Okay, so we denoted this operator as u of t comma t0. Okay, we can read it as the operator that takes the state from time t0 to time t. Now, based on arguments from classical dynamics, or based on the fundamental features of classical dynamics, we argued that in time evolution, we would like information to be conserved, all right? Or in other words, we would like our time evolution to be deterministic and reversible. And we argued that for conservation of information, normalization has to be preserved. That is, if the state is normalized, all right, or the inner product of the state with itself, bracket alpha comma t0 at time t, alpha comma t0 at time t, this has to be equal to the inner product of the state with itself at the initial time. All right, so we'll write this as bra alpha comma t0 get alpha comma t0. That is, the normalization should not change. All right, the conservation of information can be demanded by saying that the normalization has to be preserved. All right, so we gave arguments for this. Now, once we write this relation, we can immediately see that our time evolution operator has to be unitary. Right? We just have to substitute alpha comma t0 at time t by u of t comma t0 acting on get alpha comma t0. Right? So if you substitute this thing into this, all right, we get bra alpha comma t0 u dagger u get alpha comma t0 has to be equal to bra alpha comma t0 get alpha comma t0. This means that u dagger u has to be the identity operator, correct? So this we said is the unitarity condition. We said that the operator has to be unitary, right? The time evolution operator has to be unitary if we want our time evolution to be deterministic and reversible. Now, based on the preservation of normalization, we said that our time evolution operator must have the property u dagger of t comma t0, u of t comma t0 has to be equal to the identity operator. Now, there's another feature that we can require of the U operator. This is called the composition property. The composition property is simple. It says that if we are interested in obtaining the time evolution from t0 to t2, right? Obviously, we can do this by using an operator U of t2 comma t0. Okay, so initial time t0 and a later time t2. Now, the same result can be obtained by first considering an evolution from t0 to t1 and then an evolution from t1 to t2. Okay, so this is just reasonable. The only thing you need to be careful about is that we are reading this from the right to left. Right? So initially we start with the time t0 and then the operator takes it to a time t1 and then t1 to t2. Okay, so this gives us the time evolution operator from t0 to t2. So the time evolution operator from t0 to t2 can be decomposed into two parts. One, the time evolution operator from t0 to t1 and then the time evolution operator from t1 to t2. Okay, so let's see how this works. Suppose we have the initial state get alpha comma t0. All right, now we are acting on it, the operator u of t1 comma t0. Okay, obviously we know the result. By definition, this result was written as get alpha comma t0 comma semicolon t1. Okay, now let's take this state and act one more operator u of t2 comma t1 on it. All right, so here we are writing, so we are taking this and we are introducing a u of t2 comma t1 from the left. All right, so u of t2 comma t1 from the left. Here already we have u of t1 comma t0, u of t1 comma t0 acting on get alpha comma t0. Okay, this is equal to, so we haven't done much, we have just introduced a u of t2 comma t1 from the left, so that acts on the left. Here we have got u of t2 comma t1 acting on alpha comma t0 time t1. Okay. Now let's look at the right hand side. What is this result? We already know this result from definition. This is equal to get alpha comma t0 at time t2. Okay. So we have u of t2 comma t1, u of t1 comma t0 acting on get alpha comma t0 gives us get alpha comma t0 at time t2. Okay, but now again from definition we know that get alpha comma t0 at time t2 is related to get alpha comma t0 by a unitary operator of this form. So this get can be written as u of t2 comma t0 acting on get alpha comma t0. Okay, so now if you look at this, on the right hand side we have got alpha, on the left hand side we have got a get alpha comma t0 here. Here also we have get alpha comma t0, which means that these two have to be the same. Alright, these two have to be the same. In other words, let me write it here, u of t2 comma t1, u of t1 comma t0 has to be equal to u of t2 comma t0. Alright, this is the result that we have written here. It's only logical, it's only reasonable. Okay? The only thing you have to keep in mind is how to read the time, right? How to read it when you see an expression, right? So you always read it from the right. This operator takes it from t0 to t1 and then from t1 to t2. Okay? The result is that you get the time evolution from t0 to t2. Okay? Let's now consider the infinitesimal time evolution operator denoted as u of t0 plus dt comma t0. Okay, dt is an infinitesimal amount of time. Okay, an infinitesimally small amount of time. So this operator takes the state from t0 to t0 plus dt. Okay, this is the relation alpha comma t0 at t0 plus dt. The state at t0 plus dt is related to state at t0 by this infinitesimal time evolution operator. It's basically the same definition, right? Only that the final time here is t0 plus dt. Okay, which is only infinitesimally different from the initial time t0. Now we have talked about continuity. That is, we treat time as a continuous parameter. Right? We can think of arbitrarily small amounts of time. This means that the infinitesimal time evolution operator must reduce to the identity operator as dt goes to 0. Okay, so if this infinitesimal time amount of time goes to 0, that means that we are doing nothing to the system. Okay, there's no change to the system. So that's what it means when we say that limit dt tends to 0, u of t0 plus dt comma t0 has to be equal to the identity operator. Okay, if there's no time change, right? If you are not considering any time change, then the state also does not change. In other words, the state is now acted upon by the identity operator. Okay. So if dt is 0, then the time evolution operator is only the identity operator. Okay. So we can say that the infinitesimal time evolution operator u of t0 comma dt, t0 plus dt comma t0, this is almost the identity operator. Right? In other words, this would differ from the identity operator only by a small factor. Right? Only by a small factor, only infinitesimally. It will differ from the identity operator only infinitesimally. Okay. So we expect the difference between u of t0 plus dt comma t0 and the identity operator to be of first order in dt. So when we are considering the infinitesimal amount of time, right, we need to include only the first order quantities in this the first order terms in this infinitesimal quantity. Right, we need to only consider first order infinitesimal. Higher order terms can be neglected. Right, they can be thought of as 0 because dt is infinitesimally small. Then dt square, dt cube, etc. are 0 practically. Right, they can be treated or they can be neglected. Right? That's why we are considering infinitesimal amounts of time or infinitesimal quantities. So the infinitesimal time evolution operator can be written as an operator that differs from the identity operator by a small amount, right? Or by an infinitesimal transformation, if you like, by an infinitesimal amount of time evolution. Okay, so we can write it as 1 minus, or the identity operator minus a factor that is proportional to dt, the amount of time. So we said that dt is so small that we need not take the higher order terms. Since this is an operator, here we have an identity operator. The omega appearing here has to be an identity. So sorry, the omega appearing here also has to be an operator. Okay. Now, why do we write it in this form? It will become immediately clear. Let's check the condition u dagger u is equal to the identity operator. Let's see under what condition this infinitesimal operator satisfies our basic condition of unitarity. Okay. So let's put it like this. What is u dagger here? U dagger is 1 plus I omega dagger dt. dt is real. It's a small amount of time. Okay. So when we take the Hermitian conjugate, minus I will become plus I. Okay. And we have u here. So let's find u dagger u. U dagger u is equal to 1 plus I omega dagger dt multiplied by 1 minus I omega dt. Now let's multiply this, and remember, when we multiply we need to retain only those terms which are first order in dt. The higher order terms are neglected. All right, you can avoid the higher order terms because we are dealing with infinitesimal quantities. Okay? So if we carry out this multiplication, you get 1 multiplied by 1, or the identity operator multiplied by the identity operator is the identity operator itself, and then we have the identity operator multiplying this. This is 1 minus I omega dt. Okay. Now let's take this term. I omega dagger dt multiplied by 1 is plus I omega dagger dt. Okay. And I omega dagger dt multiplied by minus I omega dt. All right. So this term involves I multiplied by minus I is plus 1, omega dagger omega is omega, and dt multiplied by dt is dt square. All right. So we neglect the higher order terms. All right. This term can be neglected. These are higher order terms. We are dealing only with infinitesimal quantities, or the first order quantities in infinitesimals. All right. Now we see that this u dagger u is equal to 1 only if these two terms cancel each other. Right. Now these two terms cancel each other only if omega is equal to omega dagger. All right. So the condition for this construction or this combination to be a unitary operator, all right, is that omega has to be equal to omega dagger. In other words, the omega here is a Hermitian operator. This is Hermitian. Okay. So the idea is this. We write the infinitesimal time evolution operator as the identity operator minus I omega dt. Why do we have an I here? Because if we insert an I here, then the omega, the operator here, will be Hermitian. Okay. Without the I, this would have to be anti-Hermitian. You could do that, but we are more interested in Hermitian operators because observables are represented by Hermitian operators. Right. So this I is written outside so that omega can be Hermitian. Okay. So if omega is equal to omega dagger, then u, this infinitesimal time translation operator, satisfies the fundamental condition u dagger u is equal to 1. Okay. So we have checked that the infinitesimal time evolution operator u is equal to 1, or the identity operator, minus I omega dt satisfies the condition that u dagger u is equal to 1. Okay. We can also check whether this infinitesimal time evolution operator satisfies the composition property. Now this is what the composition property means in this context. Suppose you want an infinitesimal time evolution from t0 up to t0 plus dt1 plus dt2. Okay, we can write it as a composition of two time evolution operations. One that takes the state from t0 to t0 plus dt1, and the other that takes the state from t0 plus dt1 to t0 plus dt1 plus dt2. Okay, now we can check that this condition is satisfied. Okay, so let's start with the right hand side. So on the right hand side, here we have got u of t0 plus dt1 plus dt2, comma t0 plus dt1. Okay, so this is the initial time in this operator, and this is the final time, and they differ only by a small quantity dt2. Okay, so the difference between the initial time here and the final time here is dt2. So this is an operator that corresponds to an infinitesimal time evolution by an amount dt2, and we know how to write it. We just use this form. This is written as u of t0 plus dt1 plus dt2, comma t0 plus dt1. All right, this is an infinitesimal time evolution by an amount dt2. So this is written as 1 minus I omega dt2. Okay, similarly, u of t0 plus dt1 comma t0. This is an infinitesimal time evolution by an amount dt1. So we write this as 1 minus I omega dt1. Okay, so let's look at the multiplication on the right hand side. This multiplication becomes, if we substitute this, we have got 1 minus I omega dt2 multiplied by 1 minus I omega dt1. Okay, just multiply this now. 1 multiplied by 1, or the identity operator multiplied by the identity operator, is the identity operator itself. 1 multiplied by minus I omega dt1 gives you minus I omega dt1. Okay, now let's look at the second term. I omega dt2 multiplied by 1 is minus I omega dt2. Okay, and I omega dt2 multiplied by I omega dt1. This is again higher order. This is second order in the infinitesimal quantities, because this involves a dt1 multiplied by dt2. Okay, and this can be neglected. All right, this can be avoided. We are dealing with infinitesimal quantities, so the higher order terms are neglected. Okay, actually we can say that the higher order terms are zero in a sense. Okay, so there are higher order terms. I don't write it here. Okay. Now this is written as, this can be written as 1 minus, can take I omega common outside, and then we have got dt1 plus dt2. Okay, now what is this? This is again of the form of an infinitesimal time evolution operator, where instead of this parameter dt here, we have got dt1 plus dt2. Okay, so this is indeed of the form of a time evolution operator corresponding to a time evolution by a small amount dt1 plus dt2, and we can write this as u of t0 plus dt1 plus dt2 comma t0. Okay, which is exactly what we have here. All right, so the composition property is also satisfied if we choose the infinitesimal time evolution operator to be of this form. Okay, now we have already seen that the unitarity property is satisfied by the infinitesimal time evolution operator, provided omega is equal to omega dagger. Okay. So we have got u of t0 plus dt comma t0 is equal to the identity operator minus I omega dt. Okay, we said omega is a Hermitian operator, and we know that in quantum mechanics Hermitian operators represent observables. Okay. So is there any observable that we can associate with this operator here? Now we can get a clue by looking at the old quantum theory. Right? Over there you might have studied the expression E is equal to h nu. All right, so there's a relation between, so here is a quantity with the dimensions of frequency. You might also write this as h by 2 pi multiplied by 2 pi nu, or h by 2 pi is h bar. I can write as h bar omega, where omega is the angular frequency. Okay, again it has the dimensions 1 over time, or inverse time. So we see that we get a familiar quantity omega is equal to E divided by h bar, which has the dimensions of frequency. Okay, so maybe this omega here has something to do with the observable energy divided by a constant h bar. Okay. Now again, let's look at classical mechanics. In classical mechanics, we have seen the idea that Hamiltonian is the generator of time evolution. So in classical mechanics, Hamiltonian is the generator of time evolution, and Hamiltonian is related to the energy of the system, time evolution, all right? And it's also a generator of time evolution. Now in the quantum mechanical case also, we see that this omega appearing here has the right dimensions as E divided by h bar, okay? And energy is an observable. In quantum mechanics, observables are represented by operators. So let's introduce an operator related to the observable called energy. We'll call this the Hamiltonian operator. Okay. Now, since it's related to energy, we'll call it the Hamiltonian. So we can write omega is equal to h divided by h bar, where h is the Hamiltonian operator that represents the observable energy. So if we write omega is equal to h divided by h bar, all right, then the dimensions come out right, the dimensions here, right? Because the omega here has the dimensions of 1 over time. This also has the dimensions of 1 over time, as we just saw. So dimensions come out, right? Moreover, in classical mechanics, Hamiltonian was the generator of time evolution. So we expect that in quantum mechanics also there is a quantity, or there's an observable or an operator called Hamiltonian which generates the time evolution. Okay, so for the dimensions to come out right, we should write it as the Hamiltonian divided by h bar. Okay. Finally, we can write the time evolution operator, the infinitesimal time evolution operator, as u of t0 plus dt comma t0 is equal to 1 minus I h dt divided by h bar, where h is the Hamiltonian. Okay. And Hamiltonian is the operator that represents the observable called energy of the system. Okay, so Hamiltonian is related to the energy and it generates time evolution in quantum mechanics. So we have the time evolution operator u of t0 plus dt comma t0 is equal to identity operator minus I h divided by h bar dt. We also had the space translation operator, which we wrote as j of dx in one dimension. Let's write it as 1 minus, or the identity operator minus ip by h bar dx, where p was the generator of space translations and we called it the momentum operator. Now the next question is whether the h bar appearing here and the h bar appearing here, do they need to be the same, right? Should they be the same thing? The short answer is that yes, they are the same things, but we introduced these quantities in order to fix the dimensions. All right, so we don't immediately know that they are the same. Okay, so one way to see that they are the same is to look at the classical limit of the quantum mechanical equations. Okay, so we know that classical mechanics is quite successful in its own in the microscopic world. This means that quantum mechanics in the appropriate limit should give the same result as the classical equations. Okay, so later we'll see that if you want this equation for momentum, dx vector by dt is equal to p vector divided by m. This is a classical relation. Okay. Now the corresponding quantum mechanical relation can be shown to reduce to this classical relation in the appropriate limit. Okay, provided the h bars appearing here are the same. Okay, so the answer is yes. This is the same quantity. Let me now summarize what we have learned about the time evolution operator. The definition: the time evolution operator is defined according to this relation: get alpha comma t0 time t at time t is equal to u of t comma t0 acting on get alpha comma t0. This is the state at an initial time, say t0, and this is the state at a later time t, and these are related by the time evolution operator. Now, based on conservation of information or conservation of probabilities suggests that the normalization has to be preserved. That means bracket alpha comma t0 has to be equal to bracket alpha comma t0 at time t bracket alpha comma t0 at time t. Okay, now we say that these have to be equal. This is the conservation of information or conservation of normalization or conservation of probabilities. Okay, now we just substitute uh, this relation. All right, substitute in here using this relation and we get the condition u dagger of t1 comma t0, u of t1 comma t0 is equal to the identity operator. This is the unitarity property or unitary property. We say that the time evolution operator is unitary. Next is the composition property. The composition property says that u of t2 comma t0 can be written as u of t1 comma t0 and then u of t2 comma t1. Right? We said we have to read it from the right, t0 to t1 and then t1 to t2 will give us the time evolution from t0 to t2. Then we defined the infinitesimal time evolution operator. The infinitesimal time evolution operator. Okay, it is defined like this: u of t0 plus dt comma t0. Right? We said that we can write it as an operator that differs from the identity operator by an infinitesimal amount. So we wrote it as 1 minus I omega dt. All right, and we said that this construction is unitary if omega is equal to omega dagger. In other words, omega is a Hermitian operator. Right, so we included this I here such that the operator that appears here is a Hermitian operator. So here we have a Hermitian operator, which we can say is the generator of time evolution. Okay. Now we look at classical mechanics, and we know that Hamiltonian is the generator of time evolution in classical mechanics. So we imagine that here also we should have the Hamiltonian. But if we put the Hamiltonian here, the dimensions wouldn't be right, because we need the dimensions of this to be, the dimensions of omega to be the dimension of frequency, okay, or 1 over time. Right? So to fix the dimension, we have to write not just the Hamiltonian, but Hamiltonian divided by h bar. All right, so that's a summary of what we said. So the infinitesimal time evolution operator can be written as u of t0 plus dt comma t0 is equal to the identity operator minus I h by h bar multiplied by dt. All right, dt is the infinitesimal amount of time, h is the Hamiltonian, and h bar is our usual h bar that appears in the translation operator, for example. Okay. So this conclusion is important. We have got the form of the infinitesimal time evolution operator in quantum mechanics. Right? In the next class, we'll be building upon this basic definition. So this is an important point for us. Okay. Now there's actually a small detail that we have missed. So let's look at that, okay, for the sake of completeness. So we said that u dagger of t comma t0 multiplied by u of t comma t0 is equal to 1, and we concluded, or we said, that time evolution operator is unitary. But in fact, in order to prove that an operator is unitary, we should have u dagger u is equal to u dagger equal to 1. Right? But we have only shown that u dagger u is 1. We have not shown that u dagger is 1. Okay. So we can actually show that this is also true based on the properties that we have already discussed. Right? So let's see that. So let's look at this combination. Suppose we have got a time evolution operator u of t2 comma t1 multiplied by u of t1 comma t2. Okay, so this means again we have to start from the right. This takes the state from t2 to t1 and then from t1 to t2. Okay, so by composition property, so here we are going from t2 to t1 and then from t1 to t2. Right, so by composition property we can write this as u of t2 comma t2. And what is this? This is the unitary operator that takes the state from time t2 to the same time t2, which means that there's no change. Okay, so we can say that this is the identity operator because there's no change. This has to be the identity operator. Now let's multiply this relation from the left by u of t2 comma t1 multiplied by u dagger of t2 comma t1. All right, so we start with this expression and multiply from the left by u of t2 comma t1 u dagger of t2 comma t1. Right? And here we have got u of t2 comma t1 u of t1 comma t2. Right, so initially we have the identity operator here, but we are multiplying by this on both sides. So on the right hand side you have u of t2 comma t1 multiplied by u dagger of t2 comma t1. Okay, now using this property, right, now we can use this property, u dagger u is 1. So here we have the same combination u dagger u. All right, u dagger of t2 comma t1 u of t2 comma t1. So this has to be the identity operator by this property. Okay, so if we say that this is the identity operator, this relation becomes u of t2 comma t1 u of t1 comma t2 is equal to, on the right hand side you have u of t2 comma t1 u dagger of t2 comma t1. Okay, now what is this? Again, you start from the right. This takes the state from t2 to t1 and then from t1 to t2. So this is u of t2 comma t2 is equal to u of t2 comma t1 u dagger of t2 comma t1. What is this? This is the identity operator. Okay, so we get finally the relation identity operator is equal to u of t1 comma u of t2 comma t1 u dagger of t2 comma t1. Okay. Now to put it in the earlier form, you can write, you can say let's take t1 as the initial time t0 and let's write t2 as simply t. Okay, so we are just redefining these labels. So if you put that in here, you get the relation 1 is equal to u of t comma t0 multiplied by u dagger of t comma t0. In other words, we have shown that u dagger is also equal to 1. All right. So the conclusion is that if u dagger of t comma t0, u of t comma t0 is the identity operator, then so is u of t comma t0, u dagger of t comma t0. Okay, so we have finally come to the conclusion that u dagger u is equal to u dagger equal to the identity operator. In other words, the time evolution operator is actually unitary. Okay, it satisfies the unitarity conditions. Okay. So with that, I shall conclude this session. Thank you.